Hello, everybody. I hope you're all well. This week, I want to slowly transition into explaining further actual practical program analysis tools. And this week, I actually want to talk about Android taint analysis as we have implemented it in our quite popular tool FlowDroid. And this actually implements taint analysis in combination with a demand-driven pointer analysis. And today I want to explain what motivated us to do this and what it works and what the main tricks are to make it work. So we started this research back in the early last decade, so around 2012, 2013. This was just when Android was really becoming very popular, not just among end users, but also among organized criminals and people who actually were monetizing on data. And so there were lots of malware apps out there. There still are. It's become a little bit more under control by now, also due to analysis tools. But back then it was already an increasingly large problem. And so you saw all these news messages. And I remember when we started, there was actually the World Cup 2014 coming up, and you could really see that they had a malware campaign back then where they actually brought out a couple of malware apps that were faking to actually be officially FIFA sanctioned World Cup apps. But actually, when you installed them, they would just, suck all your data away. And back then it wasn't ransomware yet. That's still not very popular on mobile devices. But they were basically copying your data and monetizing on that. And so that was also a message back then. And so we started looking into this mobile threat landscape and what we could do about it with static analysis. And there are a number of mobile threats out there. Many of them are still current today. And so, for instance, you can have privilege escalation attacks. You can have things such as unauthorized dialing that has been inhibited a bit by security measures in the operating system. You can have insecure uses of crypto, like we already discussed with CogniCrypt, but in particular, you can and you still have sensitive data leakage, and this is what we focused on with this FlowDroid tool, and consequently what I also want to focus on in my talk today. So what you see here is, in very abstract terms, basically how FlowDroid works. So FlowDroid implements static code analysis, and what you see here on the top is basically the app, which in this case is read in binary format. So we're actually parsing the Dalvik bytecode that is contained in the APK files that are typically running on your Android mobile phone. And then FlowDroid is also configured with so-called sources and sinks. And what are sources? So in the mobile threat landscape, typical sources are sources of information that that may enter your phone. So for instance, location data, calendar data that you keep on your phone, contact data, but also SMS or MMS. Back then, these were still a thing. Today would probably be more your WhatsApp messages. And then there are also sinks, right? And these are basically communication channels through which this data can be exfiltrated off your phone. So for instance, we are looking into channels such as, again, SMS and MMS, but also Bluetooth, NFC, email, or the internet for that matter. And FlowDroid really implements this code analysis tool, so it's really a very versatile tool that you can configure with these sources and sinks. And then in the end, it reports potential privacy leaks. So in that sense, it's a may taint analysis, right? So there can be false positives, and opposed to really current tools that we have built on top of synchronized pushdown systems, FlowDroid sometimes is a bit less precise. I'll still be talking a little bit about why that is. It's still a relatively precise tool, but you can have some false positives. So that means there are potential privacy leaks. There can also be some false negatives, which has to do with incomplete call graphs, and that I will be covering as well. But in the end, the idea is really that we want to be able to determine such leaks from a given source to a given sink. And in DECA I, I already showed you this slide, right? So we are interested in knowing whether such data flows can exist. And here you can already see that this is very non-trivial to decide, because you can have all these different field accesses on the heap, and they need to be modeled properly in order to avoid false positives and nonetheless also not miss any flows. And I also showed you that we have the capability to detect such leaks through such interleaved analysis, and this is essentially how it works in FlowDroid, and I'll still be going into this in further detail on a few slides, but basically we have a forward taint analysis, which you see here in gray, coupled with a backward alias analysis, which you see in these blue arrows here. And both of them are implemented in IFDS in this case. And so they're both context sensitive and flow sensitive. And in that sense, they're both also pretty precise. So we had two main requirements when we were actually building FlowDroid, because when we built this tool, some Android taint analysis had actually already just been published. And in fact, that made it also hard for us to publish this work, in particular at security conferences, because the security reviewers, they didn't care too much about false positives or false negatives. They rather care that such a tool exists at all. And so when we tried to publish this, they were always asking us, so what's new, right? They didn't really understand the whole angle that I have on the slide, that we actually wanted to maximize true warnings. So we want to maximize the recall of the tool and also minimize false warnings. And there's a lot of algorithmics and technology that needs to be built in order to make this happen. And in the end, we therefore got this paper published at PLDI, which is a top programming languages conference. So they understand these challenges a lot better and appreciate them a lot better. And actually at PLDI, it became the top paper in this year. It has since been cited, I think, 1,500 times or even more. And it's definitely the most highly cited paper of that conference in that year. So in the end, it paid off, but not everybody appreciates this kind of work that we are doing. The other thing was we also wanted to do this fast, right? So I'm also going to be talking a little bit about how we achieved that as well. So let me first talk a little bit about maximizing true warnings, so basically maximizing recall. So how does FlowDroid obtain high recall? In order to understand this, we first have to understand the actual challenge, because if you analyze a plain old Java program, things are rather simple. So you would start at the beginning of your main method, and then you would just build your call graph from there and explore the entire program. But in Android, that's not really how it works, because if you have Android, you have a phone that you can actually interact with, and this phone reacts to your inputs, but also to inputs that come from the environment, such as incoming messages or, location changes, whatever. And so this means that actually in Android, you have this whole so-called activity lifecycle. That means any app that is running on your phone, it doesn't really have a main method at all. It's rather a plugin into the Android framework, and then there are certain callback methods that are defined here. So these are these lifecycle methods or event handlers, and these are really called by the framework at the appropriate time. And this lifecycle graphic, which you can also find in the Android documentation, it shows you the temporal dependencies between these individual callbacks, right? So the framework will make sure that when an activity starts, it will call first on create, then on start, then on resume, and so on. And then in the end, when you actually see the app running in front of you, you are in this state. And then nonetheless, the app can be paused, it can be stopped, it can even be destroyed in the end. And if it's not destroyed yet, if it's just stopped, then you can also restart it and so on, right? And for static analysis, it's actually important to understand this because in the end, this is possible control flow, right? And of course, you may have data flows through this implicit control flow as well, because data can flow, well, on the one hand, it can flow through your app, but it can also flow through the Android framework, and all of this needs to be made well, known to the analysis so that it can actually take this into account. That's particularly important because here we are actually assuming a certain threat model, right? So we are not just assuming that we want to find vulnerabilities, but we're even assuming that we want to uncover how these vulnerabilities might be exploited by attackers. So attackers are aware, of course, of this lifecycle as well, and they might exploit some of these control flow and data flow relationships for their own good, right? And so if the analysis wasn't aware of them, then immediately attackers could make use of this to try to circumvent the analysis. This is the activity lifecycle. So this is only for activities. These are basically the screens that you see in an Android app that you interact with. But there are also other Android components, such as background services, broadcast receivers, content providers, and fragments. But essentially, they all have their own life cycles, and they all look a little different, but they are modeled in the same way. So I'm not going to be talking about all of them separately. I'm just going to talk about activities, and the rest follows from there. So how do we cope with this challenge? So first of all, to show you again what the problem is and how it could be exploited by an attacker. So let's say you have an app that actually reads your device ID, so the EMI, basically at the source here, right? So that's a source method. And then it concatenates this EMI to this URL, okay? And this happens in onCreate, then in onStart, because onStart will eventually follow onCreate. If this URL is then opened and actually used in a connection like you see here, this data item can be leaked, right? Because it becomes part of the URL, so essentially it becomes part of this GET request, and therefore the data is being leaked to the server. And that's exactly what we want to detect, right? And if we had a static analyzer that would be intra-procedural, let's say, then it wouldn't detect the flow, right? Because it wouldn't cover both the procedures. It would only cover one procedure at a time. And even if it's an inter-procedural analysis, it needs to know that there can be a control flow from this method here to this method here. Otherwise, if there's no control flow edge, the leak can be missed. At the very least, if you have a flow-sensitive analysis, right, then this control flow must be known. And even if you have a flow-insensitive analysis, you still must be aware of the fact that both of these methods can be called by the framework. Then the order doesn't matter anymore, but you still need to know that they will be called. And the way we solve this in FlowDroid is by creating what we call a dummy main method. So it's really a relatively simple undertaking. So you basically model this lifecycle that you see here through an artificially generated main procedure that you see here on the right-hand side. And this will simply contain calls to the appropriate method. So that means if there is an activity in your app called myActivity, then in this case, FlowDroid will analyze your app. It will detect that this activity exists, and it will have it instantiated like you see here. And then in this case, there will be a loop. And then within this loop, we call these different framework hooks on this particular object that has been created, right? So there's an onCreate method, an onStart, an onResume, and an onPause, and so on. And as you can see here, the whole control flow is a bit more complex. So this is just a simplified example that I'm showing you here. But essentially, this is how it works. We need to take a little bit more additional care. For instance, here I'm showing you that we have initialized a parameter with null. That can sometimes be okay. In other cases, the pointer analysis that we use, it might rely on the fact that this object is actually not null. So we might actually transitively need to create some parameter objects here. So there's a bit more magic going on to make this main method more complete. But essentially, this is how it works. Now, there's still one important fact I wanted to raise. There are these predicates that you see here. So this P in particular, and down here, and there's actually another one. And these are what we and also others call opaque predicates. So this means there are predicates that should be constructed in such a way that the analysis will definitely not evaluate this predicate to true or false. And therefore, this constant true here is actually not a good choice because, for instance, in FlowDroid, which is built on top of Suit, you will see that Suit actually does, by default, even some lightweight constant propagation, and it will figure out very easily that this will then actually also always be true, and this as well. And so certain branches then actually can never be taken, right? And that's a problem because we want to simulate it in such a way that the analysis basically assumes that every single branch can always be taken, right? And we do this in FlowDroid by actually using such an opaque predicate, right? So there's a Boolean flag that we assign some value, such as this one, which we know for a fact the static analyzer will not interpret, right? So the analyzer will not know whether this Boolean is true or false. And because it doesn't know, it also cannot optimize anything here, and it will have to assume that either of these branches can be taken. And we're also not doing a path-sensitive analysis, so even if we are in the while loop here, we don't really assume that P is true, and therefore this branch will also be taken. In a path-sensitive analysis, you would have to be a bit more careful here because these path constraints would then be correlated. But here, because it's not path-sensitive, we cannot even always use the same opaque predicate in all these loops. That doesn't really hurt at this point because the correlation won't be taken into account by the analysis anyways. So this takes care of the Android lifecycle methods, but there's actually another related problem, which are so-called Android callbacks. And callbacks are additional hooks, but these hooks are not predefined. They rather are defined through the UI that make up the app. So in Android, you actually have an XML-based mechanism that people use to define certain UI elements. And these elements then can be clicked and interacted with in general, of course. And so there are a number of interaction handlers, or officially called callbacks, that are triggered by this. And so, for instance, when you click a button, that causes a certain callback to be called. And that is actually important because there exists malware, I'm showing you one here, that waits for such interactions, right? So that at least used to be very popular back then. It probably still is. So the app actually waits for something to be done within the app, and then it starts, actually downloading some files or whatever, actually executing its payload. And if we want to find this kind of behavior, then the analysis needs to be aware of these callbacks as well. Now, why is malware actually doing this? There were some very early safeguards, for instance, in the Google Play Store, where Google would just start the app and see what happens, right? And they would just see, is there any suspicious behavior? And if there wasn't, then the app was deemed to be okay. And so, of course, the app would then try to camouflage its activity by waiting for some buttons to be interacted with and so on. By now, in the Google Play Store, there's a lot more involved dynamic testing and also some static analysis. So it's not that simple anymore, but some of these mechanisms are still used. But like I said, the analysis must somehow handle this, right? And so you can have Android callbacks, like I said, defined in an XML file, right? So when you define a button in this XML descriptor, you can also define such an on-click handler here, for instance. And this is now telling Android that when the button is clicked, the send message method should be invoked, right? So this makes it explicit which particular method will be invoked when the button is clicked. And so we handle this by actually also generating into this dummy main method actually at the point where the activity is running, right? So this is the point in the lifecycle where I told you this is when you literally have the apps UI in front of you. So at this point, we actually insert these calls to this callback handler here, right? So that the analysis sees this call side and it will have an appropriate call edge in its call graph at this point here. And yeah, that's actually then giving us the desired effect. The problem is, though, that not all user interface elements are actually registered using these XML files, because there is a secondary mechanism that Android apps can use, and that looks like this. So you can call an Android API method to set an on-click listener sort of manually, right, through program code like you see here. So this here will actually cause this particular on-click callback to be called when this button B is clicked, right? And so this button is first retrieved by a certain ID that is actually also defined through this XML file, but then the Android code is used to actually register that listener. Now this we can in principle do can handle this in a similar way. So what we do here is we first construct, using this initial main method, a call graph, which you see here, and turn this into a control flow graph actually, right? And then we observe that at this point, for instance, we may be calling an on-click listener, right? Or this set on-click listener method. So we find in the initial call graph that there is a call that will register another callback. And then we analyze what kind of callback is being registered here, and we augment this dummy main method that we already have. So we regenerate this method, and we add another call to this myListener onClick method here in this case. And then we iterate this, and we need to iterate this because this listener that is registered here, this onClick method, that might of course itself register other event listeners. And so that's why we need to iterate this until we reach a fixed point, right? So in every single instance, in every single iteration, the call graph will be augmented further and further. And at some point, we will have covered all the code. And then we basically have reached the fixed point, and we can then actually start the actual taint analysis. And typically, we found that like 2 or 3 iterations are sufficient, right? And often we even don't iterate; we only do it once. It's a trade-off. I mean, you're trading off analysis time against recall in this case. And that concludes my discussion of how FlowDroid maximizes recall. And in the next video, I will be talking more about how we seek to minimize false warnings by actually maximizing precision. See you then.